So here's a short overview of my talk. So in the introduction, I'll tell you a bit about the context of this work. Then in the main part, I'll introduce a tool called HOL Spark, which is a link between the theorem prover Isabel HOL and the Spark tools. Then I'll present two applications of this link, and finally there'll be a conclusion. Let me give you some information about secunet security networks first. So secunet security networks is one of Germany's leading providers of IT security. We are a security partner of the Federal Republic of Germany. We have more than 280 employees. Our major shareholder is Giesecke & Devrient from Munich. So that's one of the world's largest manufacturer of smart cards and banknotes. We have 4 business units. So one is automotive security, the other is business security, and government and high security, the latter of which is the business unit that I'm working for. This work I'm presenting here took place in the context of the Multilevel Workstation project. The goal of the Multilevel Workstation is to process various categories of data with different classification, like secret information or information that may be disclosed to the public. And an obvious requirement for such a system is that there mustn't be any information flow between different domains. And in order to ensure this, we have to follow some design goals. So one important thing is that the trusted code base has to be kept very small. And so the multi-level workstation is made up of several components. So there are some very small components that are trusted, like an encryption or decryption service. And then there's a few larger untrusted components, like instances of Linux in which user sessions run and all the device drivers are located, and the network protocol stack, for example. And then there's a separation kernel underneath that makes sure that all these components only communicate via specific communication channels. And so all these trusted components have been implemented and verified using Spark. So for all of these components, we've verified absence of runtime exceptions, and for some of those components, we've even proved functional correctness. So unfortunately, verification is not a push-button technique. So here are some limitations. So I had a look at log files generated from our multi-level workstation code base, and I noticed that about 10% of all VCs generated from that code base are not proved automatically, which means neither by the examiner nor by the simplifier. And for some components, even up to 40% of the VCs were not proved automatically. And moreover, so in order to write down complex specifications, we sometimes require proof functions that the simplifier doesn't know anything about. So therefore, it cannot really solve VCs including such proof functions. So there's a quotation from the book by John Barnes that nicely describes the situation. So he wrote, "Despite advances in inference engine technology, it remains a fact that the human mind is capable of inspired leaps of the imagination that as yet defy automation." And that's exactly where interactive theorem provers come into play. So Isabel HOL is one such interactive theorem prover. It's already quite an old system. Its development started in 1986. By Larry Paulson, who is professor at Cambridge, and then later Tobias Nipkow, who is a professor at Technical University of Munich, joined in. And another developer is Markus Wenzel from Paris. So he's a research scientist there at one of the universities. And yeah, it's very widely used. So you surely have heard of the L4 verified project from NICTA that produced the world's first verified microkernel. And yeah, specifications in Isabel HOL are written in a kind of functional programming language augmented with logical operators like quantifiers. So if you know Haskell or ML, for example, that's pretty much how the specification language of Isabel looks like. So let me say a few words about the design philosophy of Isabel. So one important point is that inferences may only be performed by a very small kernel. So this is sometimes called the Lcf approach, and this was pioneered by the British computer scientist Robin Milner. So it's quite similar to the architecture of the multi-level workstation, where you also have these small components, and the security of the system only relies on the correctness of the small components. And in this Lcf approach, it's similar. So if the small kernel is correct, then everything that's built on top of this kernel is correct as well. So you cannot prove false theorems. So another important point is the concept of definitional theory extension. So if you introduce new concepts, then you cannot just state axioms that you would like to hold for these new concepts, but you have to define these concepts in terms of more primitive, already existing concepts. And there's also a web page that has lots of information about the system. You can also download it and have a look at some manuals and also lots of examples. So what are the advantages of using Isabel? So it has a modern graphical user interface based on JEdit or XEmacs. It also has a very expressive specification language offering data types, records, or recursive functions. All the definitions you enter into the system are checked for consistency. So for example, if you define a recursive function, then the system checks whether this function really terminates. There's a rich collection of proof methods. There are also links to external automated first-order provers and SMT solvers. And another useful thing is that you can generate executable code from specifications. So when you've written down a specifications, you often ask yourself, have I really specified the right thing? And therefore, it's very helpful to be able to generate code and then run the code on some example input. Another useful thing is that there's a counterexample generator that can detect false statements, and then this will save you a lot of work because you don't need to attempt to prove them. And finally, you can also generate documents from specifications, PDF documents that you can then show to reviewers. Also, parts of these slides have been generated using Isabel as well. So now we come to the HOL Spark link. So this is the tool chain we are using at secunet. So as usual, we start with some source files, these ADS and ADB files containing the signature and the body of a package. Then we feed this into the examiner. The examiner produces a bunch of files, which we can then feed into the simplifier, and the simplifier will output a simplified verification condition file. And then, so this will still contain some VCs that haven't been solved, and the remaining VCs we can then feed into a tool called HOL Spark. This tool takes a so-called theory file as an input. So this contains some commands loading the verification conditions and then proof scripts for proving these VCs. And, oops, sorry. And then when you've proved all of these VCs, this system also outputs a proof review file that you can then feed into the proof obligation summarizer. And then finally, you get a summary file. So that's how our tool chain works. Okay, so what are the main features of HOL Spark? So first of all, the files generated by Spark can be directly passed by Isabel. So you don't need any intermediate tools for generating theories that you then edit manually. And another important point is that the system keeps track of the proved and unproved verification conditions. So if you close the verification environment again, it will make sure that you've really proved all pending VCs. And so this link is very much inspired by the HOL Boogie link. So Boogie is a tool from Microsoft Research. And so this HOL Boogie link has been done by my former colleague, Sascha Böhme. So what are the commands offered by this HOL Spark tool? So there's a tool for, there's a command for loading and parsing verification conditions. Then there's some status command that allows you to print out all verification conditions. And yeah, then that's the most important command. So that's used to start the proof of a verification condition. So you give it the name of a verification condition as an argument, and then it will set up some proof state that allows you to prove this VC. And then finally, when you're done with all the VCs, then you can issue the Spark end command and close the Spark environment again. And then there's two more commands. So one of them is used to link Spark proof functions with Isabel functions. So you can then give a definition of a proof function inside a theory file and then link that to a Spark function. And you can do a similar thing with types. So here's some examples. So that's also taken from the book by John Barnes. That's the Euclidean algorithm for computing the sorry?
I get gloves.
So that's used for computing the greatest common divisor of two numbers m and n. Since it's a bit difficult to express what the GCD is, but just using the built-in specification language of Spark, we are introducing a so-called proof function, which I've called GCD here. And so the derives annotation just says that the output variable g is derived from m and n. And there's no precondition, but there's just a postcondition saying that g should really be the GCD of m and n. And since this program involves a while loop, we also need a loop invariant, and the loop invariant just says that the GCD of the two intermediate variables a and b is always the GCD of the input variables m and n. Okay, so here's an example of a theory that can be used to solve the VCs that are generated from this example. So each theory must have a name. So in this case, it's just example. A theory can import other theories. So in this case, it just imports a theory called Spark, which sets up everything. And now we define what the GCD is. So we first define the GCD on natural numbers. So in Isabel, there's not just integers, but there's natural numbers as well. Whereas in the FDL language, everything is integers. So we first define it on natural numbers. So this is done by recursion. That's why we use the fun command. And then we just lift the definition to the integers by first computing the absolute value of x and y, and then converting that to a natural number, then applying the GCD net function, and then translating the result back to integers. And since that definition is not so nice to work with, we derive two lemmas from that. And then finally, we link that GCD proof function from Spark with the GCD int function from Isabel. Okay, so now we haven't proved anything yet. So that's on the next slide. So the next command that we need is the Spark open command. So here we just give it the name of the verification condition file, which is called Euclid SEV. And there's two pending verification conditions in that file. So one is called procedure Euclid 4, and the other one is called procedure Euclid 9. And so that's a new JEdit-based user interface. If you move the cursor to this line, you can see that you have to prove this goal here. So that's for the preservation of the invariant. And the other goal, so this is the proof that when the loop terminates, then the variable a really contains the desired result. Okay, so let's have a look at some applications. So to motivate the application, let's have a more detailed look at the multi-level workstation. So here you can see a number of components. So one component is called the red Linux. So that's where the classified information is processed. And then there's another Linux called the black Linux, which is connected to the internet. And for obvious reasons, the red Linux and the black Linux are not directly connected, but all the packages that leave the red Linux have to go through an encryption component and then go into the black Linux, which sends them to the internet. And similarly, all packets that come from the black Linux have to go through a decryption component that then forwards them to the red Linux. And these encryption and decryption components must get their keys from somewhere, so that's what the key manager does. So this key manager does two things. So first of all, it does a Diffie-Hellman style key agreement, and the other thing it does is authentication using X509 certificates, which is needed to make sure that you've really negotiated the key with the right peer. So there are two important algorithms involved in this. So first of all, the Diffie-Hellman key agreement and certificate checking require modular arithmetic on big numbers. So Diffie-Hellman is based on some variant of exponentiation, and certificate checking is based on either RSA or elliptic curves. And for this, you need modular arithmetic. And the other important algorithm is that you need some kind of parser for extracting information from these X509 certificates. So X509 certificates use the ASN1 notation. Yeah, and both the big number library and the ASN parser used in the key manager of the multi-level workstation have been verified using Spark and Isabel. We haven't just done this because verification is lots of fun, but because bugs are routinely found in implementations of such algorithms. So for example, in OpenSSL, there recently was a bug in the ASN1 parser where you could have some buffer overflow. So now I'll try to tell you a bit about the verified big number library. So you know that public key crypto systems require computations with large numbers. So RSA typically 2048-bit and elliptic curves 320 bits approximately. And one important thing is that these arithmetic operations must be performed very efficiently. And so in an implementation, big numbers are usually represented as an array of words. And in order to reason about the correctness of such operations on big numbers, you need a way of abstracting such an array to an integer or natural number in the mathematical sense. So in order to do this, you just multiply the single words in the array with a suitable power of the basis, and then you just add up all the values. So one central operation of such libraries is modular multiplication. And a naive way of implementing that would be to use standard multiplication followed by division. But since division is very complicated, and it's both complicated to verify and it's also hard to implement and computationally expensive, there's a better approach which is called Montgomery Multiplication. So that's used in many libraries like OpenSSL, for example. So here's a small excerpt of this bignum package that we've developed. So here's some declarations. So you first define a word size, which is in our case 32. Then the base is 2 to the power of the word size. Then word is a modulo type using base as a modulus. And then begins unconstrained arrays of words. And then in order to write down the specification, we need a number of proof functions. So the first is called num of big int. So that's the abstraction function that I've explained on the previous slide. So it takes a big integer, and then that's, I think that's it's the starting index, and I is the length of the big integer. Then it returns a universal integer. So it's not just integer, because integer would be the machine words, but it's really the integers in the mathematical sense. And another function that you'll need is a function for converting a Boolean to an integer. So that's used for functions involving carries. And we also will need a function computing the modular inverse of some number x. So how does Montgomery multiplication work? So a peculiar thing about Montgomery multiplication is that it just doesn't just compute x times y modular m, but the result is also multiplied with some specific factor, which is the inverse of some constant, which I've called r. And r is just b to the power of n, where b is the basis and n is the length of the big number. So if you think of the largest big number representable using n words, and then you add 1 to it, then that's what r is. And because of the way this multiplication works, you need to transform the operands for the multiplication into a specific format, which I've called Montgomery format here. So you have to multiply that with r first, and by doing that, you can make sure that this r and inverse of r cancels out when doing a multiplication. And when you're done with the multiplication, you have to convert that back to standard format. Yeah, so this might seem like a large overhead for one multiplication, but usually you're not just doing one multiplication, but you're using that to implement exponentiation, for example, and then you're doing hundreds or thousands of multiplications, so this overhead is negligible. So let me describe in more detail how the algorithm works. So here's the usual school multiplications. You'd like to multiply x and y, and you start with the most significant digit of the first factor. And in each, so you have an accumulator that holds the intermediate result. But in each step, you shift the accumulator to the left by multiplying it with the basis. So like this. So, and let's do something slightly strange. So let's not multiply with b before doing this multiplication, but divide by b after each step. So now you get a quite similar result, but the only difference being that the result has been divided by 1,000. Now this may look rather useless because it seems to involve floating point computations, but actually we would like to do multiplication modulo. So in all cases where this number that we would like to divide by 10 is not divisible by 10, we can fix that by adding a suitable multiple of the modulus, which will not change the result, but it will make the value of the accumulator divisible by 10. So let's see how that works. So that's the algorithm, and so an important point is that the multiple, that the factor we have to multiply the modulus with can be figured out by just looking at the least significant digit of the accumulator. So here we have, so here we have a number that we'd like to divide by 10, but we can't do that. So we have to multiply that least significant digit with the additive inverse of the multiplicative inverse of the least significant digit of the modulus. So in this case, this is just 7, and 7 times 4, that's 28, modulo 10, that's 8. So we have to add 8 times 987, so 987 is the modulus. and now that's divisible by 10. Then we do it another time. So the next intermediate result is 5,208. It's also not divisible by 10. So we add 6 times 987. That's again divisible by 10. And then finally we get the desired result. So it's not quite the result we want because we have to multiply it with 1,000, but we can check that it really works. So that's an abstract description of the algorithms. So that's an algorithm that you can, for example, find in the handbook of cryptography. And it's actually not so difficult to implement that in Spark. So it just fits on one slide, if you leave out the loop invariant, of course. So first you compute this extra factor, and then the least significant digit of the accumulator receives a special treatment because it will turn 0, and then it will disappear as a result of the shifting, and also the most significant word of the accumulator will receive a special treatment because that will also disappear at the end. So let's have a quick look at the specification. So there's some preconditions and some postconditions. So the precondition just says that one of the factors, which is called y, must be smaller than the modulus. The modulus must be greater than 1. And also the inverse must have been computed in the right way. And then the postcondition says that the accumulator contains the result of multiplying x with y modulo m. So this may look a bit unwieldy, but if you write that down in mathematical notation, it looks much more compact. If you leave out all this first and last indices, then it's actually quite simple. So let's take a quick look at the formalization in Isabel. So the abstraction function looks quite similar to this definition I gave on a few slides before. Then you need some properties of this abstraction function, like a summation properties. If you have a big number which has length I plus j, you can split that up into the computation of the big number of length I and the big number of length j. And then you also need the property of the modular inverse. So let's come to the second application. So the second one is ASN1 processing. So we are using the distinguished encoding rules, DER for short. So in this encoding, data is encoded as triples containing a tag, a length, and a value. And the length just determines the size of the value in bytes. And each value can be recursively constructed of TLV triples again. So like in this example, say for a very large value that contains 2 TLV triples again, and then this value again consists of 2 TLV triples. And so comparable to an XML document, the structure of an ASN1 encoded data can be described by syntax rules. And then you can validate some given ASN1 data against such rules. So if you download some certificate from somewhere, you have a description, an abstract description of how a valid certificate should look like, you can just validate that against these rules. And one important property is that once you've validated such an ASN encoded data, you can safely access data fields in that data structure. So here's how the specification of X509 certificates looks like. So there's an RFC describing all that. So there's so that's a certificate. So the certificate consists of the actual certificate containing all the information and a signature over that certificate. And the certificate has a version number, a serial number, algorithm identifier, and similar stuff. And so this sequence can be thought of as a record having fields of different types. There's another construct called sequence of, which can be thought of as a list having elements of the same type. Now, we can easily describe these syntax rules in Isabel using a recursive data type, which I've called ASN1 syntax here. So a sequence, for example, consists of a tag encoded as a byte, and then also a list of types of the field of this sequence. And for each field, we also have a Boolean flag saying whether this field can be optional or not. The other constructor is sequence of. So a sequence of also has a tag, and then that's the type of the elements of that sequence. And then there's also a choice constructor, another one for primitive types like words or some time type or Boolean type. And then another type is any, which will just match any type. So that's also used in the X509 specification. That's why we had to include it. Now, this format that we've seen in this excerpt from the RFC can easily be translated into a definition. So that's how this would look like in Isabel. So this definition also refers to other definitions of other components like algorithm identifier, subject public key info that are defined in a similar way. So that's pretty straightforward to translate such a syntax description from the RFC to that format. Unfortunately, there are no recursive data types in Spark, so if we want to model that in Spark, we have to think of a different encoding. So one possibility is to use an array of rules, and each rule contains a child element, so that's used for these recursive constructors like sequence or sequence of. And then there's also a reference to the next element. So that's used for encoding. It's also used for encoding the different fields of a sequence of sequence construct, and also for encoding choices. And the tag is that's just an integer. Then we also need to describe what type the element has. So it can be of type sequence, sequence of, choice, primitive, or any. And then we also need an optional flag. And then this syntax is just described by an array, an unconstrained array of such rules. And so that's how a part of this X509 certificate description would look like in Spark. And it's also straightforward to translate the abstract specification to that one. So here's how the validation code looks like in Isabel. So that's essentially a large functional program that does lots of case distinctions. So you first try to decode a single TLV triple, and then if that goes wrong, you just reject the input, and otherwise, if that doesn't go wrong, then you have to recursively validate other values, and you can actually run that on certificates that we're using for our multi-level workstation. So in order to prove that the Spark code does the same thing as this is functional implementation, we have to relate the different representations of the ASN1 syntax rules. So we have this array of rules with references to other rules, and we have this recursive data type. So we need a kind of correspondence predicate relating these two representations. And the correspondence predicate is just defined by recursion over the data type representing the syntax rules. And then this will be used in the correctness statement. So here's the correctness statement of the validation function. So that's also contains the signature of the function. So you give it a syntax description, then a starting rule, then the actual data, which is an array of bytes. Then the first the index of containing the first data element and the length of the data, and it will just return true or false. And there are some preconditions for that. So one precondition says that the syntax rules have to be well-formed, and if this function returns success, then it must have successfully validated it. And so the definitions of these proof functions essentially use the Isabel functions, the correspondence predicate, and here you also, so one problem is that the validation function is recursive, and since Spark doesn't have recursion, you have to model some kind of stack, and then this precondition says that the stack size needed to validate against those rules is less than the maximum stack size that I've declared when compiling the program. And so the postcondition also uses this correspondence predicate and this validation function defined in Isabel. So here's a short comparison of these two applications. So the big number library has about 1,398 lines of Spark, of which 549 lines are annotations, so that's 39%. And we have 2,309 lines of Isabel code, which is about 1.65 lines of Isabel code per lines of Spark, which is not that bad. And that's because the control flow and the invariants are relatively simple, but on the other hand, it involves quite intricate mathematics like number theory. And on the other hand, the ASN1 library has 814 lines of Spark, of which 284 are annotations. That's about 34%. That's comparable to the big number library. But we have 3,673 lines of Isabel code, which is 4.51 lines of Spark, lines of Isabel per lines of Spark. That's a bit more than the big number library. That's because the control flow and invariants are rather complicated in this application, and the lack of recursion in Spark complicated the code of the validator a little bit. But on the other hand, there was no difficult mathematics involved. So let's come to the conclusion. So according to our experience, verification of industrial scale software is possible with reasonable effort, but interactive proof turned out to be indispensable for more complex properties. And sometimes people claim that verified code is slow, but it's actually not, so it's quite comparable with non-verified code. And this HOL Spark verification environment is already part of the Isabel distribution, and it's used for many applications at secunet. And for more details, you can have a look at some paper at the System Software Verification Workshop in 2011, which contains all the details about this big number library. And you can also download the code of the big number library, so it's part of the libspark crypto library. So we briefly mentioned some related work. Okay, so there's also some future work that we are thinking of. So we've also used this big number library to implement a library for elliptic curve cryptography. Currently, we've just proved absence of runtime exceptions, but we'd like to prove full functional correctness as well. And we're working on a tool for translating descriptions of finite automata to Isabel HOL and Spark. So actually, lots of these components in the multi-level workstations are just finite automata. And we would like to verify security properties of the key manager as well. So thanks for your attention.